right, hello math fans. All right, so this is chapter 4B, and this is day 1 homework. Okay, so let's start out with the first problem here. And this is page 226 to 227. All right, and this is 1A. Okay, the problem says finding numbers. The sum of two non-negative numbers is 20. Find the numbers if, and we're doing A, the sum of their squares is as large as possible. So, first of all, they give you one piece of information. So you say x plus y is equal to 20. And then it says the sum of their numbers is as large as possible, or sum of their squares. So we're trying to maximize x squared plus y squared. Okay? And we're also trying to minimize that. That's the two parts to it. All right? Okay, so first of all, that's our function right here. F of x equals x squared plus y squared. And what I want to do is I need it in terms of one variable here, and so I'm going to solve for y, for this guy right here. I get y equals 20 minus x. And then I'm going to substitute that in for y here. Because I want it in terms of one variable, then I can take the derivative and do my interval testing and find my maxes and mins. All right? So f of x equals x squared plus 20 minus x squared. All right, and you can take the derivative directly here because you guys know how to do that. So f prime of x equals 2x plus 2 parentheses 20 minus x to the first power, and then of course the chain rule times negative 1. All right, so I simplify that. F prime of x equals 2x plus, well, this is going to actually be minus, right? Minus 40 plus 2x. All right, so simplify a little more. F prime of x equals 4x minus 40. So that's first derivative. Set that equal to 0 to find our critical points, and we get 4x equals 40, x equals 10. All right, so we do our interval testing here. 9 and 11, and we get minus and plus. So it's minus and plus. That makes this guy right here a minimum value. All right, so with these kind of problems, they're closed interval problems. And the reason they're closed interval problems is because you can have one of your answers to be 0. Okay? In an open interval problem, which is really like most application problems, you can't have an answer of 0. For example, like the dimension on a rectangle or a box, you can't have a dimension of 0. It's impossible. So it's an open interval. Okay, and you don't have to worry about testing the endpoints then. With this one, I can. So what I'm going to do is, if I test x is 0 and y is 20, because right, it has to equal 20, and I plug it into x squared plus y squared, I get 0 squared plus 20 squared, and that's equal to 400. If I plug in 20 comma 0, so x is 20, y is 0, that's 20 squared plus 0 squared, that's equal to 400. And then my y value that I found, right, this is the minimize, it's 10, and then of course the x was 10, so the y is also 10, and that gives me 10 squared plus 10 squared equals 200. So again, they're not asking you for x and y per se. What they're doing is they're saying give me two numbers. So if you want to minimize it, so the sum for as small as possible, well, that's what we just figured out. That's the 10 and the 10. So the two numbers are 10 and 10. To the sum where it's as big as possible, it's 20 or 0, 0, and 20. It doesn't matter. So the answer is 0, 20 and 0. And that's your answer for number 1. All right. Number 3, maximizing perimeter. It says, what is the smallest perimeter possible for a rectangle whose area is 16 inches squared, and what are its dimensions? All right, so first of all, we have area is equal to length times width, and that's equal to 16. And then we're trying to, the smallest perimeter, so we're trying to minimize the perimeter. And the perimeter of a rectangle is 2L plus 2W. So this is my function, guys, right here, that 2L plus 2W. So what I can do is I need to, I'm given L times W equals 16. I need to solve for one of the variables. So I'm going to solve for L, and I get L equal, divide both sides by W is 16 over W. And then I'm going to substitute that into there. So I have my perimeter in terms of W is 2 times 16 over W plus 2W. All right, so I simplify that. P of W is equal to 32 over W plus 2W. And then I can take the derivative, so P prime of W is equal to negative 32 over W squared, just use the quotient rule, plus 2 equals 0. All right, and then move things over, so negative 32 over W squared equals negative 2 over 1. You cross multiply, so you get negative 2W squared equals negative 32. So W squared equals 16, so W equals 4. Of course, you don't have to worry about the plus or minus 4 because you can't have a negative width. All right, so let's do our interval testing here. So 3 and 5, and this gives us negative, and this gives us positive. Remember, we're plugging back into this guy right here, the derivative, to do the interval testing. So this makes this a minimum value, which is exactly what we're trying to do here. We're trying to minimize the perimeter. All right, so there we go. I don't have to check endpoints because, again, it's an open loop problem, or open end, so there are no endpoints. And so the width is 4 inches, and the length, well, length is 16 divided by 4, so 16 over 4, which is 4 inches. All right, and then they ask you what are the dimensions, and they say what is the smallest perimeter. Well, the smallest perimeter is just right 4 times 2 for the width plus 4 times 2 for the length, so that's equal to 16 inches for perimeter. Okay, that's not too bad. All right, let's go on to number 5. 5 is just a little more involved because they give you a picture here, but you kind of have to remember a few things about your right triangles, basically. Okay, so it says inscribing rectangles. The figure shows a rectangle inscribed in an isosceles right triangle whose hypotenuse is 2 units long. Okay, so here's the picture here. And they give you a rectangle here. And they give you this. This is -1, this is 0, this is +1. And they give you this as a right triangle right here. Okay? And then this is P of X, comma, question mark, because we don't know that value. All right. And, okay, so a couple things that they give you. First of all, this is my XY axis. Let me draw it in here. All right, this is my XY axis. And as you know, an XY axis, this is a right angle also. Okay, so this, they give you, it's an isosceles right triangle. So if it's an isosceles right triangle, hopefully you guys agree that this is a 45-degree angle here. So this is really a 45, 45, 90 triangle. Well, if this is 45 degrees, and then if I look at this triangle right here, I'll use a highlighter. If I look at this triangle here, okay, that's also a 45, 45, 90 triangle. It's got to be, right? Because this is a right angle here. That's already 45 degrees. And that's actually kind of important. The reason that's important is because if this length here is equal to 1, that means this length is also equal to 1. All right, and so that coordinate right here is 0, 1. That's actually pretty important because we need to come up with an equation of a line. In fact, that's the first thing. It says express the y-coordinate of P in terms of x. Hint, write an equation for the line AB. And this is AB. So it says write an equation for that line. So what I can do is, well, obviously, if this is 0, 1, that's this coordinate right here is 1, 0. The slope is going to be just using the yax, right? y2 minus y1 over x2 minus x1. It's just going to be -1. And your y-intercept is 1. So b is equal to 1. So the equation for A is going to be y is equal to -x plus 1. Okay, that's pretty easy once you actually draw everything out there. All right. The second part, it says express the area of the rectangle in terms of x. Okay, so the area, if this distance here is x, right? It even gives you, there's your p parentheses x comma question mark. So this distance, I'll use another color here to make it a little more obvious. Okay, this distance is x right here. So do you guys agree that I have x over here, but I also have x over here? So the area is equal to 2x, and this is just going to be my y value. Okay, that makes sense because you have to have an x and you have to have a y, and we have to have it in terms of x and y. So it's 2x times y. So anyway, my area comes out to be, if I substitute this in, it's 2x times -x plus 1. So area is equal to -2x squared plus 2x. All right? And, okay, so that's it for B. Express the area in terms of x. C is what is the largest area the rectangle can have and what are its dimensions? Well, I have a nice little area formula here, and I just do, so this was B. And C is A prime is equal to -4x plus 2. Set that equal to 0, so 4x equals -4x equals -2, x equals 1/2. All right, so that is the value of x. Again, let's test it here. We'll do it up here. It's 1/2, and we're supposed to be maximizing this. So again, it's an open interval, so we don't need to test endpoints. In fact, all the problems we're really going to be doing now are open interval unless it literally says, hey, give me some numbers that are maximizing and minimizing numbers where a number can be 0. Okay, anyway, we got 1/2, and we're going to do 0 and 1. So this is going to be plus and minus when you plug in the derivative. So it's going to be a max. So that's our maximum value, and right, our y value, here's our old y equation right here. So y equals -1/2 plus 1, which is 1/2 also. So the dimensions, I'm running out of room here, dimensions are of that rectangle. First of all, you guys agree that the x, it's 2x, so it's 2 times 1/2, which is 1. That's one dimension, and the other dimension is the y value. So it's 1 by 1/2. Those are the dimensions. Okay, and then the area, which is, it says, what is the largest area and what are the dimensions? So the area then is 1 times 1/2. So area equals 1 times 1/2, which is 1/2 unit squared. Okay, that's it. That was kind of a trickier problem. Had to think a little bit about it, but that's what you have to do. All right? Okay, let's move on to the next one. number 6. It says a rectangle has its base on the x-axis. Okay, so it has its base on the x-axis, and its upper two vertices on a parabola y equals 12 minus x squared. Okay, so this is basically what it looks like. Okay, and the parabola is like this. Not a great picture, but good enough. Okay. So it's two upper vertices around this parabola, and this parabola is y equals 12 minus x squared. Okay, what is the largest area? So we're maximizing area. What is the maximum area the rectangle can have, and what are its dimensions? Okay, so with this one here is we know our area equals length times width. And in terms of x and y, this coordinate here is x comma y. Okay, because it's on this parabola. All right, so that's got to be x comma y. So that means this distance right here is x, and this distance here is also x, and this distance here is y. All right, makes sense. So area equals length, which is 2x. 2x, and the width is the y. Okay, and so area is equal to 2x times y, which is 12 minus x squared. So area equals 24x minus 2x cubed. And then I take the derivative. It's a prime, this is a prime of x, right? In terms of x, is 24 minus 6x squared. We set that equal to 0, so 6x squared is 24, x squared is 4, x equals 2. All right, we do our interval testing here, and this is going to be, this is going to be 1, this is going to be 2, and this is going to be 3. Okay, so we test it and we get plus here and a minus here, so that makes it a max, which is exactly what we're looking for. So they ask us again, what is the largest area the rectangle can have? Well, that's 2, and what we have to do is we have to find the value of y, right? So y is equal to 12 minus 2, so y equals 10. Sorry, I keep losing this squared here. Okay, 12 minus x squared, so 2 squared, so it's going to be 8. So the dimension is 8 by, well, it's 2x though, right? So it's 8 by 4. That's my dimension of that rectangle. And then the area, of course, equals 8 times 4, which is 32 units squared. All right, not too bad. All right, let's move on to number 7. Optimal dimensions. You are planning to make an open rectangular box from an 8 by 15 piece of cardboard by cutting congruent squares from the corners and folding up the sides. What are the dimensions of the box of the largest volume you can make this way, and what is its volume? All right, so this is the picture here, math fans. Okay, I'm cutting out these corners, so then when I fold it up, I can actually make a box. All right, and each of these that we're cutting out are all x length. And the deal is this guy right here is 15, and this guy right here is 8. So these little parts right here Well, this one is going to be 8 minus 2x, and this one is going to be 15 minus 2x. All right. So let's start with our volume of a rectangular box is going to be length times width times height. All right. So if I get the volume of this one is going to be the length is 15 minus 2x, and the width is going to be 8 minus 2x, and the height is going to be x, right? Because when you fold that up, right, this distance right here, it's going to fold up to be an x height if I fold all those up. That's pretty important to understand that. All right, and then if I multiply all this out, I'm just going to kind of spare you the algebra here. You guys can do that, but you get 4x cubed minus 46x squared plus 120x. All right, and then I'm trying to maximize the volume, and so I get b prime of x is equal to 12x squared minus 92x plus 120 equals 0. And if I factor that, I wound up getting two answers. I get x equals 5/3 and x equals 6. Now you need to look at this. One of the answers is impossible. 6 is impossible because you can't, just looking at one edge here, this one edge over here, you can't have 6 and 6 because you only have a maximum length of 8, so it's impossible. So this one's out of there, and your answer is 5/3. Again, we always do our interval testing. So you have 5/3 here, and 0 and 2. So this is plus and this is minus. So it's a maximum value. Okay, and so I'm going to get my length then, because they ask you for what are the dimensions of the box, of the largest box. And so this length is 15 minus 2x, which is right there. So it's going to be 15 minus 2 times 5/3, which comes out to be 11 2/3 inches. And then the width is this distance right here. So it's 8 minus 2 times 5/3, which comes out to be 4 1/3 inches. All right, and then our height is just the value of x. So the height is equal to 5/3 or 1 2/3 inches. Right, and the volume is just all those multiplied together, and that gives you 90 and 20/27 inches cubed. All right, so that wasn't too bad. Okay, number 9. Okay, number 9 says the best fencing plan. A rectangular plot of farmland will be bounded on one side by a river and on the other 3 sides by a single strand electric fence. With 800 meters of wire at your disposal, what is the largest area you can enclose and what are its dimensions? All right, so really the picture here is you have 3 sides and this is water here. Okay, so I don't have to worry about this. And so I have a width and I have a width and I have a length. So the perimeter of this is 2W plus L, and because I gave you the amount of wire, that's what the perimeter is. Okay, and I'm trying to maximize the area. Good, it's really a good problem. Okay, because you may even have something like that in the future where you're given so much fence, and you're trying to figure out what's the maximum amount of area I can have for your, let's say, for a dog staying in the fence. Okay, and you don't want to, you can only spend so much, or you only have so much fencing, you want to maximize that area. All right, and it might be against your garage, so this might be the exact same problem. So the area of this, of course, is length times width, and what I'm going to do is I'm going to solve this guy right here for L. So L is equal to 800 minus 2W, and I'm going to plug that into there. So we're trying to maximize area, so my A sub W equals 800 minus 2W times W. So that gives us 800W minus 2W squared. All right, and then I take the derivative of that. A prime of W is equal to 800 minus 4W. So, and that set that equals 0. So 4W equals 800. W equals 200 meters. Okay, we're going to do our nice little interval testing. And it doesn't really matter. We can do 100 and we can do 300. And this is going to be plus here and minus here. So this is a maximum value. And so our width, that's what it is. They're asking for the width. So the width is 200 meters. And the length is, we already have an equation right up here, right? 800 minus 2 times 200. So length equals 400 meters. And then the area is just, to find out the area, is just 200 times 400, which is 80,000 square meters. All right, not too bad. Let's go on to number 10. It's a little bit different. The shortest fence. A 216 meter square rectangular P-patch is to be enclosed by a fence and divided into 2 equal parts by another fence parallel to one of the sides. What dimensions for the outer rectangle will require the smallest total length of fence? How much fence will be needed? Okay, so what dimensions for the outer rectangle will require the smallest total length of the fence? So this is the setup for this one. Okay, so it's one rectangle, but it's split up by another fence here. So we're going to call this Y. Each of these are Y dimensions, and this dimension right here is your X value. Okay, they tell you it's the area of the patch is 216 meters squared, and basically the area is X times Y, so that's equal to 216. All right, and what we're trying to do is we're trying to minimize the perimeter. All right, and the perimeter is just, in the perimeter, we're trying to minimize the perimeter of the whole thing, right? So the perimeter is equal to 2x plus 3y. All right. So let's solve. We got this equation right here. Let's solve for, it doesn't matter, I'm going to solve for x. X is equal to 216 over y, and then I'm just going to substitute that into there. So P, now it's going to be P of y, right? P of y is equal to 2 times 216 over y plus 3y. So P of y equals negative 430 or 432, positive 432 over y plus 3y. All right, then we're going to take the derivative. So P prime of y is using the quotient rule, so it actually turns out to negative 432 over y squared plus 3y, or plus 3 equal, and then we're going to set that equal to 0. Okay, so we get 432 over y squared equals 3 over 1. We cross multiply and we get y squared equals 144. So y equals 12. Okay, we do our interval testing. 11 and 13. And this gives us negative and positive. So this guy right here is a minimum value. Okay, which is good. We're trying to minimize the amount of fence we're using. All right. So if y is the we figure out what y is, Well, isn't x just 216 over y? So it's 216 over 12. So x is equal to 18. All right, so the dimensions are going to be 12 meters by 18 meters. And then the total fence, because we're trying to see how much fence we're using, it's 3 of the y's, so 3 times 12 plus 2 of the x's, right? One here and one up here. So 2 of the x's, so 2 times 18, and that gives us 72 meters. That is the perimeter that we're going to use, the minimum amount of fence to use. All right, not too bad. All right, number 14, vertical motion problem. This is actually kind of mellow. The height of an object moving vertically is given by s equals negative 16t squared plus 96t plus 112. All right, with s is in feet and t is in seconds, find the object's velocity when t is equal to 0. Okay, this is kind of like back in the day, guys. The object's velocity is just the first derivative. So v of t is equal to negative 32t plus 96. All right, and we set that, or it says, let's see, find the object's velocity when t is equal to 0. Okay, so we just have v of 0. That's negative 32 times 0 plus 96 equals 96. So it's 96 feet per second. Okay, that's A. B is find its maximum height when it occurs. And okay, so it's maximum height. In order to find the maximum height, we're basically, isn't that when t is equal to, or when the velocity is 0? So when v of t equals 0, that's the maximum height. And think about it, if it's position, and I want to know the maximum position, isn't that taking the first derivative, which really is the velocity, right? Okay, so what we're doing is taking v of t equals 0, which again is our first derivative, so it's negative 32t plus 96, set that equal to 0. So solve and you get t is equal to 3 seconds. Okay, but they want to know what the position is when the velocity is 0. That's why it's a little bit of work in here, but not a big deal. The maximum height when the object's velocity, the maximum height and when it occurs. All right, so it occurs at 3 seconds, and then the maximum height is you just plug it back into the original problem. So s of 3 is equal to negative 16 times 3 squared plus 96 times 3 plus 112. So s of 3 is equal to 256 feet. That's the position at 3 seconds when the velocity is 0. So that's your maximum height. All right. And last one is C, which is find its velocity when s is equal to 0. Okay, so what we need to do is we need to set the position equation equal to 0. So negative 16t squared plus 96t plus 112 equals 0. All right, and again, it's factoring, but anyway, it turns out to be after you factor, you get t is equal to negative 1 and 7 seconds. Well, obviously, it can't be negative 1, so the answer is the time is 7 seconds. Okay, but they want to know what the velocity is at that time. So it's v of 7 is equal to negative 32 times 7 plus 96. So v of 7 is equal to negative 128 feet per second. Okay, so kind of be careful what they're asking for. Just remember velocity is first derivative. If I say what is the velocity when the position is 0, then you set the position equal to 0, find the value t, plug it into the velocity equation, etc. All right, so that isn't too bad. Okay, last one is number 16. And it says, designing a can. What are the dimensions of the lightest open top right circular cylindrical can? That's a mouthful. That will hold a volume of 1,000 cubic centimeters. Okay, so the key word here, guys, is the lightest. Okay, lightest means the minimum amount of steel that you're going to use. So you're minimizing the surface area. That's what it means when it's the lightest can, right? It makes sense. You're using the least amount of steel. All right, so that's actually pretty important. Another thing here, it says it's an open top cylindrical can. Okay, so let's use our volume equation. The volume is equal to pi r squared h. And you guys remember, pi r squared is the area of the base, and height is the distance between the bases, right? That's for the volume of a cylinder. And that is equal to 1,000. So I want to minimize the surface area, which, if you remember, it's pi r squared. That's one bottom, because it only has one bottom. If it was 2, it would be 2 pi r squared. But it's pi r squared, and then the distance around, I'm just going to draw a cylinder here real quickly here. The area of, let's just actually talk about the bottom. Okay, that area is pi r squared. And then this, if I open this cylinder up, and again I'm trying to have you guys remember the formula, but if I open the cylinder up, it would actually be a big rectangle, and the distance around that would be the length of that rectangle, which is the circumference. Okay, and the circumference is 2 pi r. So really, the surface area or the lateral area of that is 2 pi r times the height. So it's pi r squared plus 2 pi r h. Okay. And I'm minimizing that. I already have this nice little friendly equation here. And what I can do is I'm going to solve. You want to solve for the easiest variable. I mean, if I solve for r, that's kind of brutal to plug back into here. So I'm going to solve for h. So h is equal to 1,000 over pi r squared. Okay, that's pretty mellow. And then I'm going to plug that into this equation. So surface area is equal to pi r squared plus 2 pi r times 1,000 over pi r squared. Okay, and the pi's cancel, this r cancels with that r, and I have pi r squared plus 2,000 over r. That's my surface area, and I'm going to do that in terms of S sub r, or S of r. Okay, and then again I'm trying to minimize the surface area, so I'm going to do S prime of r, and that's equal to 2 pi r minus 2,000 over r squared using the quotient rule. Set that equal to 0. So I get 2 pi r equals 2,000 over r squared. And I cross multiply here, and I get, bring it over here. Okay, I get r cubed times 2 pi equals 2,000. And I get r cubed equals 2,000 over 2 pi. It's kind of a messy number, but that's okay. It's just going to deal with it. And we get r is equal to, oh, sorry, it's divided by, this cancels. So I get, let's simplify that. So I get 1,000 over pi. So r is equal to 10 over the cube root of pi. Okay, and if I simplify this guy, it's about 6.83 centimeters. That's not a very realistic way to present that, is 10 over the cube root of pi. Okay, so that is, and that's what they're looking for here, I believe, with 16, is they're saying, what are the dimensions? So the radius is 6.83. We have our height, which is back over here. So h equals 1,000 over pi. and it's this number squared, so about 6.83 squared, and that comes out to approximately same thing, 6.83 centimeters. Okay, so those are my dimensions. That's my height and that's my radius. The last part of the problem actually asks you to compare the results with the results in example 4. And the deal is, in example 4, you had a top and a bottom. Okay, and it's kind of a cool thing in that you have a top and a bottom. So what happens is this dimension that we're having is, it's a little bit shorter. For this problem, it's a little bit shorter. I'm going to write this down. It's shorter and wider. Now, the nice thing about that is, one of the reasons why it can be wider is because I don't have to worry about two bases. I only have to worry about one base. Now, the wider it is, the bigger that top has to be, the more material that has to be used. But if I make it shorter, for no top, I can make it a little bit shorter and a little bit wider, and I only have one base to deal with, but then I have less lateral area. So this is a little bit, they're compensating for no top for this problem by making it a little bit wider and a little bit shorter. Okay? Anyway, that's day 1, math fans. It's kind of a lot of stuff, but you know, it's definitely good practice for optimization problems. All right, that's it, math fans. Have a nice day. Goodbye.